Hello, I'm Armin Weiß from Universität Stuttgart, and today I'm going to present you my results on equations over finite solvable groups. So these results are based on the exponential time hypothesis, and under the exponential time hypothesis I will show some lower bounds for equations in finite solvable groups. Equations over algebraic structures like rings or fields have a really long history in mathematics. So for the case of groups, this is also true for abelian groups. So here the most basic example is the integers with addition, so the infinite cyclic group, and well, equations could look like this or that or something like this. And here, of course, we see the first equation doesn't have a solution. The second one here, everything is a solution. And in the third one, it has a solution, but not everything is a solution. Now, in a general group, the equation could look like this. So first we have some constants, and we have variables, and we have inverses of variables. And of course, in a group, we always can multiply by the inverses. So we can assume that the right-hand side of the equation is actually 1. So the equation is of the form alpha equal to 1, and alpha is an expression over constants, variables, and their inverses. And now, of course, if we have such an equation, there are two basic questions we can ask. The first one is equation satisfiability. Here, the input is an expression, as before, and the question is whether there is a satisfying assignment. So whether we can assign values to the variable such that the whole equation evaluates to 1. So here, sigma is extended in a natural way to the whole equation. And the second problem is the equation identity problem. So again, the input is an expression, and the question is whether all assignments are satisfying. So, and in both these cases, I always assume that the group is not part of the input. So the group is always constant. And as we have seen before, equations over the integers are just linear equations, so of course they are decidable. But there are also many infinite groups where these problems are not decidable. But in this talk, I only focus on finite groups. And of course, here everything is decidable. So actually, equation satisfiability is an NP, because if I have an input expression, then I can guess for every occurring variable value in the group G. And then I just, well, multiply the values together from left to right, and this gives a value in the group, and then I just check whether it's 1 or not. So equation satisfiability is an NP. With the same argument, we can see that equation identity is in co-NP. But, well, what about finite classification with respect to complexity? Are there groups where this is NP complete or not? So before I say something to this question, let's start with a simple observation. So the equation identity problem is rather easier than the satisfiability problem because we have this Turing reduction. So if equation satisfiability is in polynomial time, then so is equation identity. Now the reduction is quite easy. So we have an input expression, and then, well, for each non-identity element of G, we just check whether alpha G inverse is satisfiable. And if alpha G inverse is satisfiable, then of course alpha equals to 1 is not an identity. On the other hand, if alpha is not an identity, then there is some non-identity G such that alpha G inverse is satisfiable. So we have this reduction. Now let's go to the history of complexity results over finite groups. So first, Goldman and Russell showed in 2002 that if G is nilpotent, then equation satisfiability is in P. And well, because of the previous remark, this also applies to equation identity. And if one looks in their proof carefully, then one sees that this actually can be done in the small circuit class ACC0, so constant depth with modular gates. And Goldman and Russell also showed that if G is non-solvable, then the equation satisfiability problem is NP complete. So here, it's a nice characterization. So here it's very easy, and here's difficult. And actually, this was extended later to the equation identity problem, showing that it's co-NP complete if the group is non-solvable. But, well, there's still this gap here between nilpotent and non-solvable. So they're all solvable but non-nilpotent groups. And, well, we know that equation satisfiability is an NP and equation identity is in co-NP. And since these results, many other results appeared for some special cases showing polynomial time algorithms in these cases. And I only want to mention the last one, so it's early this year, and it shows that if we have a P group, semi-direct and abelian group, then equation satisfiability is in P. And if we have a nilpotent group, semi-direct abelian group, then equation identity problem is in P. Yeah, so this is slightly more general than here. But, well, of course, these are not all solvable non-nilpotent groups. Actually, all these groups have fitting lengths too. So I'm going to tell you later what fitting length is. So, but of course, this asks, what about all the other solvable but non-nilpotent groups? And in this talk, I'm going to prove some lower bounds for some sufficiently complicated ones of these. So usually for showing NP hardness, we reduce some NP complete problem to a problem. So like 3-sat to equation satisfiability. And for doing so, well, we need to encode the conjunction and disjunction into the group. And usually it turns out to be useful to encode the false by the identity in the group and true by something non-identity in the group. And now consider the following puzzle. So we have 2 nails in the wall, and then we have a picture which is attached to a rope, and we want to put the rope around the nails so that the picture falls down as soon as we remove one of the nails. Yeah? So this is like a conjunction. If both nails are in the wall, the picture stays, but if one nail is removed, the picture falls down. So here you can see the picture. Now I remove one nail, picture falls down a little bit, but in the end it stays. So we try a different way. First we wrap it around the first nail, counterclockwise, and counterclockwise around the second nail. Now clockwise around the first nail, and clockwise around the second nail. And now let's try. So as you have seen, the commutator of 2 elements can serve as this conjunction. Yeah? So because if x or y is equal to 1, then of course the commutator is 1. And if x and y are both not 1, then the commutator could be something non-identity. But of course this depends on the group also. Okay, now I want to present you 2 of my friends, which will serve as examples for groups in this talk. The first one is the symmetric group of 3 over 3 elements. So we can also think of it as a symmetry group of this triangle. Yeah, so we have 3 reflections, the exchanging 1 and 2, or 2 and 3, or 3 and 1. And then we have these rotations, just rotating the whole triangle. And yeah, we can also write this as 3 as a semi-direct product, C3, semi-direct C2. So C2 are reflections and C3 are the rotations. And we can also write it as a quotient of the free group, then just the reflection square is equal to rotation cube is equal to 1. And we have this relation. Yeah? If you first do the reflection and then do a rotation, it's the same as if you do first the rotation in the other direction and then the reflection. And with this rule, we can actually compute the commutator. So we take the commutator of a rotation and a reflection. So that's just written out here. And then we apply this rule here. And this gets d inverse, and d inverse times d inverse. That's just the same as d squared, and that's the same as d. Now the other example group is this group, G648705. So it's a extension of the symmetric group of 3 elements. So we take 3 copies of S3 and take the semi-direct product with C3. And if you count the number of elements, it's 648, that's this number, and the 705 is the index in the GAP small group library. And here the semi-direct product is defined with this shift multiplication. So if we conjugate by A, it means that we shift the different components. And we can view this group as a permutation over 9 elements. So the S3 each permute 3 elements each, and then this A permutes these whole sets of 3 elements. Okay, now the commutators. Yeah, as already written down, that's a commutator, and the iterated commutator is defined like this. And now a group is nilpotent of class C if and only if all iterated commutators of length C plus 1 are 1. So that's a theorem, but for us it serves as a definition. And now the fitting length of a group, also called nilpotent length sometimes, is the smallest k such that there is a sequence of normal subgroups, n0 and 1 and so on, such that each quotient of two successive normal subgroups is nilpotent. So that's very related to the derived length of a group. For the derived length, we would require that the two successive quotients are abelian. So that means the fitting length is always less or equal than the derived length of a group. And now the fitting length of this S3, it's just 2, because we have the normal subgroup C3 in S2, and the quotient is C2, which is abelian. And it's not 1 because S3 is not nilpotent. And the fitting length of Gstar is 3, because we have this series, and both quotients are abelian again. So before I come to the main result, let me define the exponential time hypothesis. So exponential time hypothesis means that there is some constant delta such that there is no algorithm for 3-sat which needs time less than 2 to the delta n. And n here is the number of variables. And because of this sparsification lemma, we actually can assume that n is like also the number of clauses, so that we can assume that the number of clauses is linear. And altogether, that means there is no 2 to little o of n plus m time algorithm for 3-sat under exponential time hypothesis. Now we are ready to state the main result. So let G be a finite solvable group and either assume that the fitting length of G is at least 4, or the fitting length is 3, and we have this extra condition saying that there is no fitting length 2 normal subgroup of G, which has an index of a power of 2. And if one of this condition applies, then equation satisfiability and equation identity cannot be decided in time 2 to the little of log square n. So here capital N is just the input size, so the length of the input expression. And well, this implies that equation sat and equation identity are not in P under exponential time hypothesis. So this gives the first lower bound for the solvable but non-nilpotent case. Now here in the fitting length 3 case, we have this extra condition, which is a little technical. And it's reasonable to ask, maybe we can remove it. And actually, there is an example of a group which doesn't satisfy this condition, but still equation sat and equation identity are not in P and ETH. So actually, a few days after submitting this paper to ICALP, another paper appeared, and here Itzia, Kavalek, and Kraszkowski showed that equation sat of S4 and equation identity of S4 are not in P. So S4 is the symmetric group on 4 elements. And it has a fitting length 2 normal subgroup of index of 2. That's the A4. Of course, I also recommend you to watch this talk at LIX. So it goes also beyond groups to universal algebra. Now let's look into the proof of the main result. For showing hardness, we reduce the C coloring problem to equation sat and equation identity. So a C coloring of a graph is just a map V to some set of colors, and we say it's valid if 2 endpoints of an edge are colored with different colors. And well, the C coloring problem is there valid C coloring? And of course, it's well known that this problem is NP complete. And actually, under the exponential time hypothesis, it can be shown that there is no 2 of little o of number of vertices plus number of edges algorithm, unless ETH fails. Okay, now as a first step, we won't do the actual reduction, but we do a much simpler reduction. So we reduce the 2 coloring problem to equation sat of S3. So of course, 2 coloring is actually in polynomial time, and also equation sat of S3 is in polynomial time. So this reduction doesn't show anything, but it gives an idea of how the actual reduction works. Okay, so we start with a graph gamma, and over vertices 1 to n, and we have some edges, which are 2-element subsets of the vertices. And now we want to reduce the coloring. So it makes sense to introduce a variable for each vertex. This variable should represent the color. So for each vertex, we introduce a variable xi. And now for each edge, I and j, we set alpha k is equal to xi xj inverse. Yeah, so if the two endpoints of the edges, if they have the same evaluation, this alpha k will be 1. And if they have different evaluations, this alpha k will be not 1. And then we set beta equal to the iterated commutator of this d. D is the rotation from before, and all these alpha I. Yeah, so that's just the iterated commutator. And now the claim is that beta equal to d is satisfiable if and only if gamma is two-colorable. And let's prove this. So recall the structure of S3. So we have this normal subgroup C3, and the quotient is C2. And now let sigma be an assignment to the variables. And given the sigma, we can define a coloring to actually a two coloring. So a map from V to 1 and 2. And the color should be 1 if and only if sigma of xi is in C3. So if sigma of xi is in C3, the vertex is blue, otherwise it's red. And now let's look at this commutator. Sigma of this commutator is 1 if sigma of alpha 1 is in C3. Because if sigma of alpha 1 is in C3, then it's a commutator of a rotation with another rotation, and it's inside a abelian group, so this is 1. And we already calculated before, the commutator of a rotation and a reflection is actually just the rotation. So we have this. And now we know that this is the case. So sigma of alpha 1 is not in C3 if and only if the two endpoints of the first edge have different colors. And so that means this innermost commutator, it evaluates to something non-identity if and only if the first edge is colored in a correct way. And now we just apply induction. So the whole commutator will be non-identity if and only if all edges evaluate to some are colored correctly. Yeah? And otherwise, if there's one edge which is not colored correctly, then the whole commutator will collapse and be 1. Yeah? So this shows the reduction. Now this reduction, it has even another problem, which I still haven't told you. So because the length of beta, it's very long. Yeah? It's actually exponential. Yeah? If you write down, so the commutator, it's here just an abbreviation. So if we write it down as a full word over the generators and the variables, we see that it's exponential. Yeah? So its length approximately 2 to the m. So that's another defect. Okay, now let's switch to the real reduction. So we take this group Gstar. Here again the structure. And again we have an input graph with vertices 1 to n. And again we assign to every vertex one variable xi. And now what we do is we group the edges into roughly square root of m groups of square root of m edges each. And now of course each edge gets two indices, because one is for the group and one is the index within the group. And now we do the same as before. We say this alpha I or alpha KL here, and we set it's the variable of the one vertex and the inverse variable of the other vertex of this edge. And now we do again as before. Now we do this for every group. We introduce this iterated commutator beta k. It's just a now here, instead of the rotation, we take the reflection in the first component and second and third component identity, and then this iterated commutator with all these edge gadgets of this group. And then we also take this conjugation with a new variable yk. That's somehow for technical reasons. And now finally, we set gamma is again an iterated commutator. Here we take the rotation again, and in the third and second component identity, and well, then the iterated commutator with all these gadgets we previously defined. Now the claim is that gamma equal to D11 is satisfiable if and only if gamma is 3 colorable, so capital gamma. And well, the proof of this, it's more or less the same as before. It's a little more technical, but I think you can believe me. Now, the essential step here is that these beta k's, they have length now 2 to the mu. That's exactly the same calculation as we have seen before. But now the good thing is that mu is not m, but it's only square root of m. Yeah? And now gamma, well, it's again an iterated commutator of length mu. So and each individual item in gamma, it has length at also 2 to the mu. So we get a total length of gamma of approximately 2 to the mu times 2 to the mu. So which is roughly 2 to the 2 square root of m. And now we can construct a contradiction to ETH. So assume equation satisfiability is decidable in time 2 to the little of log square n, so where n is the length of the input equation. Then we can solve 3-coloring actually in time 2 to the little of n plus m, because we just plug in this n equal 2 to the 2 square root of m. That's just this size here. So we just compute the reduction, and well, and then we just have to do the math here. So 2 to the little of log square times 2 to the 2 square root of m. We can simplify it, and we just get 2 to the little of m. Well, and that contradicts ETH. So this is the proof of the main result in case of this group Gstar. So the actual proof of the most general result is, of course, more technical, but all central ideas are here already present in this proof. Well, now let's just summarize. So we gave a quasi-polynomial lower bound for equation satisfiability and equation identity if G has fitting length 4 or fitting length 3 and some other conditions. As I said, these conditions are not met for the group S4, but there are still the lower bounds under ETH. And actually, together with my Polish colleagues, we plan a paper showing a general lower bound for all groups of fitting length 3. Well, now, of course, there are still some open questions, especially what about the groups of fitting length 2? So we have seen there are many results for some special groups of fitting length 2 that there the problem is in polynomial time, but the general question is still open. And of course, also we gave some lower bounds. Now the question is, of course, are there some matching upper bounds? So is equation satisfiability and equation identity decidable in quasi-polynomial time? So with this question, I want to conclude, and thank you very much for your attention, and I hope to see you in the question and answer session.